folks, and welcome to another exciting episode here at BMW. As you can see, I'm relaxing on my sofa after a particularly not so stressful day of soldering. So let's see, what I want to update you guys on is the status of the inverter project that I've been building based upon the design from Johannes Hubner, and give you guys a bit of an update on what's been going on with the Panzer as well. So basically about maybe 3 weeks ago now, had a bit of a Panzer problem. And that particular Panzer problem led me to a new project. Now I know I need another project, like I need a hole in the head, but I got one whether I wanted it or not. So what happened? Well, it's kind of difficult to define the exact cause, but what I've narrowed it down to is that in the inverter in their Panzer, or as I should properly say, their Panzer, I had a loose connection on one on one IGBT gate terminal, and that's bad. That IGBT floated and we had a problem. So what it ultimately cost me was one CM600DY12NF IGBT brick, and HCPL 3120 driver, and a DC to DC converter. But I got it fixed and the Panzer is moving around again just fine. But it led me to some thoughts about the inverter and maybe some potential fault conditions that could arise. And as you guys know from the Lexus hybrid gearbox project that I'm working on also, I've been in communication with Michael Elias, and he made some suggestions to me about the gate drivers that I was currently using in the inverter, and some potential pitfalls that could occur with such a basic gate driver. So I went around looking and I found a much more capable driver chip that had a lot more protections built into it. It's another Avigo part, the ACPL 337J, I believe is the part number. I'll verify that in the next clip here. But this part then, of course, was not exactly pin compatible with the existing driver board. So I decided, what the hell, let's design a new driver board for our IGBT half bridge modules, and got myself some boards here, and here it is. I'll give you guys a close-up on this. But this is a PCB. It's quite nice, compact size. It's a mainly surface mount card. There's some through-hole components, most noticeably the two DC to DC converters. So I got this guy designed, and I got a bunch of them from Seed Studio in China, and just today I got a chance to build one fully and test it on the bench, so we'll be showing you guys that shortly. Now, one of the many features in this particular chip is that it provides two error condition outputs on on a TTL digital line. One of them is called UVLO, which is under voltage lockout. So if the 5 volt supply to the board drops below, I think about 4.55 volts, the driver is shut down. And the other one is a more general fault pin, and that fault pin basically triggers, particularly if there's a desaturation event on the IGBT, and it locks out the driver until such time as the power is recycled. Now, if we had simply taken these cards that I had designed and put these into the inverter, they would work fine, but we would have a few more potential problems. If one of these driver chips were to detect a problem, such as a desaturation event on a particular IGBT, it would of course shut itself down and trigger the relevant fault pin. But the problem is that on the existing logic board for the inverter, there would be nowhere to connect that pin, or indeed the pins from any of the 3 of these driver boards that we would have on the inverter to send that particular signal back in such a way that we could have both a hardware shutdown of all 6 PWM channels and also signal the microprocessor that we have a problem. So I figured, you know, in for a penny, in for a pound, I've redesigned the IGBT driver board. Let's redesign the logic board. And I did that. We've got a new logic board. So I'll go through this in more detail shortly, but one of the big changes that I made is I got rid of the IDC plugs on this, and all of our I/O channels now go through one of which are rapidly becoming my favorite plugs, is a 35 pin Tyco amp seal plug, which directly mounts onto the PCB and gives us not only a much better access to our various pins, but is a very sturdy mounting for the entire logic board if we wish to mount this on a casing somewhere. So I'm currently building the first one of these, and it's just I've cleaned the thing up and added some extra features such as the amp seal socket here, just to make it a slightly more user-friendly version. But there's more, and one of the features about this inverter that I kind of love to hate was the way that it measured the high voltage DC bus on the DC link voltage, and I loved it because of its simplicity, but I hated it because it didn't provide galvanic isolation between the high voltage battery and the normal 12 volt systems in the vehicle. So if I've redesigned 2 boards, let's redesign all 3, and went ahead and redesigned the sensor board. So biggest change to the sensor board is that we now use a, what's the part again? It's an Avico ACPL C87A, I believe, device to give us galvanically isolated high voltage DC bus measurement. And I suppose the next biggest thing is we've got two nice big holes here, and this is to allow us to actually board mount two LEM 800 amp current sensors, which basically go on like so, and bolt onto the board securely with 4 M3 bolts. So that here is our 3 redesigned board sets for our inverter, and I think this should improve it quite a bit and make it a lot more user friendly, and also mean that with our IGBT driver being a lot more intelligent, it should mean that particularly during testing and software development and working stuff out, it's nearly inevitable that some way, somehow, you're going to turn on 2 transistors at the wrong time. And with this driver board, I would hope that that should be fairly impossible. So why don't we take a close look at the boards, and then we'll have a look at the test that I've just rigged up on the bench, and I'll let you guys get back to watching funny cat videos, so stay with us. Alrighty, so a bit of a close look at some of our boards here. So this guy is our new IGBT driver board, and it uses the ACPL 337J driver chip, and has support for desaturation detection and various other protection mechanisms on both channels, and is pinned to use the Murata MGJ series of DC to DC converters, which are specifically designed for IGBT gate drive applications. They provide a -5 volts and a +15 volts rail, and have, I believe, 5.2 kV of DC isolation strength. So they're a much better part for this application. And as you can see, it's a mostly surface mount card, and we have some capacitors on the back side of the board that enables us to get them as close to the pins of the driver chip as we can. And the mechanism that we're using for connecting these boards to their parent are the means of Molex SL series crimp headers that you'll see in the next segment, and they work quite well. Also on the silk screen here, you'll see that all of the pins are clearly marked, and that's a big help for diagnostics and for building as well. So that's our IGBT driver. We'll be seeing more of this guy soon. So what's next is this is a bare logic PCB, and again, as I mentioned, we've done away with the IDC headers. This is still a fully true hole board. I decided to leave it that way for ease of home building, which I think will be still pretty much mainly the method. I would like to think that at some point I could convert this to a surface mount card and get it made in small volumes by a PCB manufacturer. And so again, what we've done here is we've got a port for where the sensor board connects, and we've got our 3-phase connections here, again with all of the pins clearly marked. We've our provision for our 35-pin amp seal connector. I'll show you guys now. This is a partly populated board. I've just started to lay some of the components on it. For example, there you'll see this is where the Olimex daughter board fits on, and there's our 35-pin amp seal providing all of the I/O lines necessary to run the inverter. That's logic board. And lastly, by no means least, we have our new sensor board. Again, this is pretty much a 95% true hole board. The only surface mount part being the ACPL C87 bus measurement device, along with just a few 0.1 mic 0805 caps that need to be surface mount, just so that they get to be as close to the pins of the part as possible. Again, you'll see the clearly marked I/O port, and we're using a very wide pitch screw terminal here. This is 7.8 millimeter pitch. Oh, it's not gone yet. This is for where we connect our high voltage, and our goes in here, and this is our voltage divider here to scale the DC bus down to what the chip can measure. And this is a Molex SL header box here, and these give a very secure and a very simple and cheap way to interconnect the various boards. You can just use twisted pair Ethernet cable crimped onto the Molex pins, and as I explained in the other video, I've done away with the various options for the current sensors. I'm just sticking with the Haas HTFS 800, which now mounts directly to the PCB for added strength, mechanical strength, and just ease of assembly also. Okay, so for anyone who hasn't gone completely asleep yet, here's our first build of the driver board. We've got it currently hanging onto a CM600DY12NF IGBT, and you'll notice here these two yellow test leads are on the collector connections on the driver board, and they are connected to collector 1 and collector 2 on our IGBT. And I've just left them as clip leads just for convenience, and so I can simulate a desaturation event to test that the lockout in the driver chips works. So basically what this will be monitoring for is a condition where the VCE of the IGBT exceeds a certain point when the device is fully turned on. And if that happens, it means the transistor is in a bad place, and it needs to be shut down. And indeed, these chips contain a soft shutdown system that will relatively slowly close down the transistor so that we don't get any inductive kickback on the high voltage bus. So again, it's pretty much just a hand assembled card. It's gone together very well indeed. There's nothing particularly strenuous. The smallest parts are 0805, so it's all very easy to hand solder. I don't have any special soldering equipment, just a pair of simple tweezers and a fairly small point on a basic 25 watt mains soldering iron. So what I'm going to do is going to give you guys a very quick demo here of it actually working. Okay, so I've got the rig powered up. We've got a bench power supply here supplying 5 volts to the driver board. Currently drawing 154 milliamps, and on our scope here you can see that we've got our gate emitter on. I believe the top side transistor is currently at -5 volts. Got a signal generator here set up to about 8 kilohertz on a 50-50 duty cycle. We're taking a signal from its TTL output, and just for the purposes of a test, feeding that to both channels on the driver board. So I'm going to turn that on. And straight away on the scope, we'll see that our gate emitter is now swinging -5 plus 15 volts at 8.53 kilohertz. And our current on our power supply has jumped up to 318 milliamps at 5 volts. So why don't I get you guys a bit of a closer look at that scope screen there. So there we have it. It's very nice drive signal. We can zoom in on it a little bit to see that we're getting some very good, nice fast transitions on our gate emitter. Admittedly, there's no bus voltage on there at the minute, so that'll be part of our next testing. And there you have it, folks. There is a bit of an update on the whole inverter project. We're making good progress on it. Our next real job is just a lot of soldering and working out the bill of materials. And yeah, let's just get it built and test it and see how the thing works out for us. But it's been a learning experience. Probably could well, maybe do without, maybe not. I'm glad that it's happened in one way, because it's kind of made me do some of these changes, which should make for a better system anyway. So as always, folks, thanks for staying with me, thanks for watching, thanks for your kind comments, and we'll see you all soon.